Throughout history, people have used various simple machines such as pulleys, inclined planes, or levers because they make certain tasks easier. They do that by providing what's called mechanical advantage, also sometimes called leverage. I like to think of mechanical advantage as the idea of trading distance for effort. And today I'm going to look at some scenarios involving pulleys and different pulley systems to demonstrate the idea of mechanical advantage or trading distance for effort. Let's pretend I have a box that has a weight of 300 newtons and I want to lift that box. With no pulleys, to lift this box, it would take 300 newtons of force. We'll assume it's being lifted at a constant velocity, meaning that my upward lifting force is balancing the downward weight or the downward force of gravity. So to lift 300 newtons, it would require 300 newtons of force up on my part. When lifting, I am exerting a force over a displacement, meaning that work is being done on the box. Furthermore, work is defined as change in energy. So as work is being done on the box is actually gaining energy. And in this scenario, throughout the lifting process, the height of the box is changing, meaning that gravitational potential energy is being gained by the box. Let's pretend I want to lift this to a height of 1 meter. Exerting 300 newtons of force across 1 meter of displacement would give me 300 joules of work, meaning that the box would gain 300 joules of gravitational potential energy in the lifting process. This would probably be the most difficult way to lift this box a meter from a force perspective. You would have to, you're bending over, you're using your legs, your back, whatever, and it takes 300 newtons of force to get the box up. Now, to make my life easier, let's pretend I rig a pulley to some fixed point above that box. So this is going to feel easier, but it isn't actually any easier in the sense that I still need to exert 300 newtons of force to lift. So this box still needs 300 newtons of upward force to lift it. And all the pulley in this scenario does is redirect that force. The tension on both ends of a rope has to be the same always, assuming massless ropes and massless frictionless pulleys. So I need to pull this way with 300 newtons of force in order to get 300 newtons of force up to lift the box. Now this feels easier because instead of lifting with my legs or my back, I can pull on this rope and I can use my own body weight to kind of get behind that and lift. So this feels easier, but I'm still exerting 300 newtons of force and I still would do 300 joules of work lifting this box 1 meter. Let's switch it up a little bit more and let's get a couple of pulleys going. So this rope is anchored to a fixed point above the box, and then I have a pulley here, and then I would pull this way. If you analyze this situation, you will see that this box is really being lifted by 2 ropes. Each one of this bit of rope is engaged. If either one of those pieces of rope were to break, the box would no longer be lifted. So we basically just say, there's 2 ropes acting. In this scenario, because I have 2 ropes acting, I only need to pull with 150 newtons of force to get 150 newtons in this rope and 150 newtons in this rope to get the necessary 300 newtons in order to lift. So did I just create free energy? Is anything in life ever free? No. What's happening here is I'm trading distance for effort. I can pull with 150 newtons and I can lift something that's 300 newtons. But as I pull on this rope, the change in height of the box is actually going to be smaller. In this scenario, if I pull the rope 1 meter, because the rope doubles back here, if I pull the rope with 1 meter, this box is only going to raise half a meter. Let's look over at this system once again. If I pull this rope 1 meter, this box goes up 1 meter. So in this scenario, I pull with 300 newtons of force. I exert that force over 1 meter, and I would do 300 joules of work to lift this box. Over here, I'm only exerting 150 newtons of force. But for every meter that I pull this rope, I only get half a meter of displacement. So in this scenario, to lift this box to a height of 1 meter, I would be exerting 150 newtons of force across 2 meters of displacement, because this rope would have to get 2 meters shorter in order for this box to lift 1 meter. If I exert 150 newtons of force across a 2 meter displacement, I have still done 300 joules of work. Let's go to one more example. Slightly more complicated, added a few more pulleys. I anchored the rope to the box now, sent that over a pulley, sent that over a pulley, and then I had one more pulley just to redirect the force back down. In this scenario, I have 1, 2, 3 ropes now engaged. I have 3 ropes helping this box go up. This means it's only going to take 100 newtons of force on this end to get each one of these ropes tensioned to exert 100 newtons of upward force to lift my 300 newton object. However, putting 100 newtons of force in, getting 300 newtons of force out, definitely is less effort. That means I need to exert the force now over an even longer distance. Look at how much more rope is involved in this system, how many times it curves and doubles back, compared to this system. Over here, every meter I pull on this rope, I shorten each one of these ropes a little bit. Every meter I pull here results in only 1/3 of a meter in height gained by the box. So in this scenario, if I wanted to lift this box to a height of 1 meter, I would have to pull this rope for 3 meters. So if I pulled with 100 newtons of force across a displacement of 3 meters, I would still do 300 joules of work. This box would still get lifted to a height of 1 meter. In all of these videos, the task done was the same. I wanted to lift a 300 newton object to a height of 1 meter. In all of those scenarios, the work done was the same because the same amount of potential energy was gained. The task was always the same. 300 newtons of weight was lifted to a height of 1 meter, and 300 joules of work was done in the process. However, depending upon how I rig my pulleys, I can either get no mechanical advantage and I can exert the most force for the least amount of time, or I could get a little bit of mechanical advantage and exert a little less force over a slightly larger displacement, or I could exert 1/3 the force that I would have in this scenario, but I would have to exert that force over 3 times the displacement. So at the end of the day, this might feel easier, but I'm doing the same work no matter what.